Some further examples. Now, I didn't get so far in the preparation. Okay, so we're looking at del Pezzo surfaces. Over number fields. And you remember del Pezzo surface has a degree, the self-intersection of the anticanonical class. And the degree is in the range 1 to 9. So just to give you an overview of where we are in the whole classification scheme and how it relates to arithmetic questions, when the degree is at least 5, then a del Pezzo surface over a number field always satisfies the Hasse principle. So that leaves degrees 4, 3, 2, and 1. Now, degree 1 del Pezzo surface always has a point, the base point of the anticanonical linear system. So this always has a rational point. So that leaves this intermediate range, degrees 2, 3, and 4, where there is a potential for Bauer-Manin obstruction to the Hasse principle. Okay, so yesterday we were looking at examples of degree 2 del Pezzo surfaces with a focus on 2 torsion elements in the Brouwer group. So this was yesterday. So it's natural to ask, and what sorts of groups you get, what higher torsion elements you might find in general. So this is for degree 2, and these were particular examples. Now, what's known in general is that for degrees 3 and 4, there's only 2 and 3 torsion only. And indeed, there are many examples, both in degree 4 and in degree 3, of obstructions to the Hasse principle, coming from 2 and 3 torsion elements of the Brouwer group. Now, in degree 2, there can be higher torsion. So there's also, and this appears in the work that I did with Yurichenko, there is an example in our paper of a 4 torsion. So yeah, we work with a 4 torsion element in the Brouwer group, but the analysis is quite difficult. So I didn't prepare it for today, and I think that's just as well. So what I'm going to talk about today is an example with 3 torsion, just to give you a sense of well, something other than quaternion algebras, but not something so difficult as the analysis of the 4 torsion elements. So this is the plan for today. Okay, so there's an analysis done by Kolyotelen, Kanievsky, and Sensuk. '87, and they consider degree 3 Del Pezzo surfaces, that is, cubic surfaces, and they focus on a particular form, and it's a diagonal form. And they analyze this and produce examples where there is Brouwer-Manin obstruction to the Hasse principle. So let me outline a little bit of what they do. And then at some point, I'll make a simplification on what they do. So first of all, they want to study rational points. So over the number field Q, so A, B, C, D are integers. All non-zero. And the first observation is that there are rational points if and only if there are points valued in the quadratic extension gotten by adjoining cube roots of unity. Now, there's nothing special. Well, this is a general fact for any quadratic extension. Essentially, if you had a point valued here, so it's a conjugate pair of points, you draw the line through those points, and it meets the cubic surface at some other point, and that will necessarily be defined over Q. So this is a very simple statement. But the reason for picking this quadratic extension is because now, if you start adjoining cube roots, when you solve for the equations up to 27 lines on the cubic surface, you'll have cube roots of these various coefficients. And when you adjoin cube roots, if you just start with Q and adjoin a cube root of some number, that extension is not even Galois. So it's harder to work with. But if you start with the field K, Q adjoin cube roots of unity, and now start adding cube roots of numbers, what you get are cyclic extensions. Okay, so in fact, the splitting field is some polycyclic extension, and the Galois group is 3 copies Z mod 3. And they're able to compute the Picard group. And this is in the generic case. Okay, so now their analysis actually uses central simple algebras of a rather complicated sort. So their analysis. Oh, no, I blanked out. Though this was just me not writing the correct thing. Yeah, that was. Yeah, I guess to be correct, let me put a little K here. So their analysis uses Galois-Kalmagi. Bicyclic extensions. So they, in fact, they're able to cut down to a degree 9 extension, but still, that's some big co-cycle data. Rather unpleasantly large central simple algebras and very complicated analysis. So in the spirit of yesterday's lecture, we want to use as small a field extension as possible. And, well, it's the same story I talked about last time. You try index 3, in this case 3, not 2. You try index 3 subgroups of the Galois group, and we find a cubic extension. And it turns out you would join cube root of AD over BC. Such that the inflation map is an isomorphism. So for the smaller extension, if you compute the H1, this is Gal. And then Picard. We have the inflation map to the H1 of the full Picard group for the big group here, which is isomorphic to the Brouwer group mod Brouwer of the field. And we find an isomorphism. Well, now we proceed as we did yesterday. So you have to find divisor defined over this cubic extension, having the right class. So some divisor. So this is like yesterday. And then finding a rational function. Where is H? H is defined over K. So now we have E and we have its two conjugates. Like that. And so this gives rise to a cyclic division algebra. So you take the function field, join two non-commuting variables with the relations R cubed is AD over BC. S cubed is this rational function H, and S moves past the R and at the expense of the cube root of 1. Okay, so this is also like yesterday. And then now, yesterday we had quaternion algebras, and now we have cyclic division algebras for extension of degree 3. Okay, so we want to proceed as much as possible like we did yesterday. So it's easy to determine whether at a periodic point the algebra is trivial or non-trivial. That's essentially just using, it's a cyclic group, so we have a very efficient resolution to compute group cohomology for cyclic group. And essentially it just amounts to determining whether an element of some p-adic field is a norm or not. So we have some local invariant. Alpha, let's say, is this class. So this generates okay, so the local invariant takes the values 0, 1/3, or 2/3, and we can very easily sort out these two cases. And in some simple cases, it may be enough for the analysis to know just whether an algebra is trivial or not. But in general, the Brouwer-Mannon obstruction involves a sum of local invariants. And for your sum, to compute the sum accurately, you can very easily be in a situation where you need to know whether the local invariant is 1/3 or 2/3. And that's a harder problem. So more challenging. To distinguish local invariant 1/3 and 2/3. So I'll explain one approach to doing that. Okay, so we need two preliminary bits. Yeah, so how you get a central simple algebra from co-cycle data. So we have some Galois extension, and we have a co-cycle for the group G, so that's a collection of field elements satisfying the co-cycle condition. And let's take a co-cycle for the standard resolution. I mean, if you work with an efficient resolution, you can then get maps back and forth to the standard resolution. So you can quickly convert a co-cycle with respect to some more efficient resolution to a co-cycle with respect to the standard resolution. So explicitly, that's for every g and g prime in G, you have a number epsilon g prime, and they satisfy the co-cycle condition, which I'll just write it down. So the product of this factor and this factor acted upon. So this is how I'll denote action of a Galois group element on a field element. Then this is some product. Okay. So these data determine central simple algebra. So the algebra is copy of G copies of so these are just these are just symbols. So one is the use of identity, and then so these are the names of generators of the algebra, and then I have to tell you how they multiply, and they multiply with these epsilon factors. And then how you multiply by field elements, UG times some field element, let's say beta, is you act on beta by the Galois element. Okay, I should mention this description is one of several choices. There are other choices that you can have some differing conventions. Even the co-cycle condition you might see written with different left versus right conventions. But let's just fix this. So this will be the central simple algebra associated with 2 co-cycle. Okay, well, let's see an example of this. want to keep that. Okay, so example, we take k as before, and we adjoin a cube root. Cube root of d, and we consider the following cocycle. Where h is an element of k. Then this gives rise to an algebra over k cube root of d. So let's call this r. Then we have r cubed is d. And let's call, we have s. S will be the name for the group, the generator coming from this, how you want to think of your cyclic group. If you think 0, 1, 2, then associated with 1. So the U there coming from this column. Then S squared you just read off is 1 times, is 1 times then the generator for the element 2 in the group. And then if you S cubed, you pick up this H. And now this last rule tells you that S moving past a field element, such as R, is, so you act with the Galois group, and the Galois group sends R to R times cube root of unity times S. So in fact, you match the description that we had. Okay, now we need to understand the local invariant of a central simple algebra. Over a p-adic field. Okay, so we assume that we have a p-adic field. Let's call it k nu, where nu is a non-Archimedean place of k. And then Brouwer of, the whole time so for people who work in algebraic number theory, is this a V or a nu? When you have it's a V, okay, so I've been saying the wrong, okay, so this is a place called V. Sorry, so I guess I've been making this mistake for quite a while. Apologies again. When it comes to notation, I mean, I've made a number of mistakes, and well, it's just okay. Lack of preparation, I guess. But so KV has I mean, I have sort of a chance to write things up properly for the proceedings, but then there's the record of this. So yeah, you'll just, anyway. So this is, I assume this is, no, okay. So most of you know more about local class field theory than I do. So this is familiar to all of you. But, well, it wasn't familiar to me, so I'll describe it so that I can then understand it. If you have, no, an example, or should I just do, okay, I'll just say quickly in general. So there is a unique cyclic extension of some degree. So let's fix some, I don't know. I hope I'm not going to cause more trouble with notation. So there's a unique cyclic extension of degree. No, I'm getting everything wrong. Unique, I forgot the most important word. Unramified, well, extension, which ends up to being cyclic of degree m. It's cyclic. So let's call it like that. And Galois and a canonical is the one that acts by Frobenius. So on the level of residue fields, you would have some finite field here, and then you would have some finite field like that. And so there's a unique generator that acts by Frobenius there. And so this is you're fixing a convention, because that's just how this is defined. So let's see maybe an example. So, yeah, so you want a cyclic extension of Q2. Now, at least over the rationals, I only know one cyclic extension, and that's a root of x cubed minus 3x plus 1 equals 0. So this is usually, I think, the first example that you see of a cyclic extension of Q. So if you have Q, and then if you look at the real subfield of Q adjoin ninth root of unity. So this is cyclic. So, and well, yeah, if you take e to the 2 pi I over 9 plus e to the minus 2 pi I over 9, that's a generator. And then if you look at the Galois group and you see how it acts, you see that alpha goes to alpha squared minus 2. So this is action of generator of Galois group. And then notice mod 2. So it's Frobenius. Okay, so now yeah, actually I just realized, so yeah, I might get something wrong later. Well, I probably will get something wrong later, so yeah, sorry about that. Okay, so then fact is that every division algebra over the p-adic field KV of, I put it in the wrong place. Every division algebra of order dividing M is split by the extension. That means you tensor to this unramified degree M extension, and the division algebra becomes isomorphic to a matrix algebra. Okay, so then the way to compute a local invariant is so sorry, this is sort of a review of standard material, but to compute local invariant. So you express your algebra by describe the algebra by a cocycle for the cyclic extension. And then apply so you have now an element H2. So this is G. What's G? The Galois group of this extension. And now you apply an isomorphism. So from cohomology boundary map from exact sequence, and because Q is divisible, the terms involving Q are 0, so this is an isomorphism, and then H1 and there's no group action here, so it's a H1 for trivial group action. I mean, if you just go through the cocycle condition is the condition to be a homomorphism, so this is homomorphisms. And now the Galois group we just saw has a canonical generator. So you apply the canonical generator, and you get an element of Q mod Z, and that's the local invariant. No, just so now the thing I realize I'll get wrong is that this is for Q2, but now, when you complete K at 2, you get a quadratic extension here. And so, I mean, it's still this extension, but now the Frobenius should be alpha to the 4th. So I think I'll have to take, I might be working, I think I'm working with the wrong generator anyway. Well, I can fix it by just multiplying by 2. I guess I'll do that. Then I should get the right thing. So, okay, well, let's look at the example. So, so finally, the example we'll do, and this is from the paper, Kolio, Tallinn, Kanievsky, and Sansud. Particular coefficients, 1, 5, 12, and 30. Okay, now there was, it's got erased now, but this is the cyclic extension, k join cube root AD over BC, and AD over BC is 1/2. So we have our k join cube root of 2. And then there was the procedure outlined, and you get your h. Actually, you do it twice, so you get 2 h's. So we have generator alpha. And AI is an algebra just like this, so AI. And these HIs, well, they're just rational functions with coefficients in k. So something like H1 is 95 plus 165 theta x squared y plus 24. And H2 is and again, there's the cheat I'm using. These aren't rational functions. You get rational functions by you divide by just pick your favorite, x cubed or any variable cubed. Put that in the denominator. And since multiplying by a cube has no effect on the algebra that you get, so I'm just using this abuse of notation. Okay, so we have the division algebras. Now we do local analysis. So the two added points, so we have for each x2. Yeah, and here's where, so you can work, well, I just work with two-adic points because it's enough to just obstruct the rational points with this algebra. So then we solve this equation in the algebra. And actually it's enough to work with just one. I mean, they're equal in Brouwer group, so you just pick the one that's better for the analysis. So the second one is in fact the one that works. So this means we have this means that we get an inclusion of this degree 3 extension of the completion of k at 2 into the algebra. And then we want these epsilon factors. So we then solve for some these UGs, well, whatever, UGs. And then we have this well, whatever it is. Then we compute well, whatever here, sigma. You take the generator of the Galois group and you cube it, and you get some field element. And then you apply the valuation. So here I think I made the mistake, and actually you should use the square of that generator. Anyway, I think so you get valuation 1, mod 3. Hence local invariant, if I'm right. And so actually, I mean, you have to do some two-adic analysis here where you show, so you compute H2 at two adic points. You get something, you get sort of a constant residue class, mod 4, and then you show that you can, and anyway, you can sort of carry out this and show that on that residue class you get constant here. Okay, and then the three-adic analysis. And so it turns out now it's more convenient to use H1, and you evaluate H1 at x3, and you always get a norm. So a norm for the extension.
So you always suppose that your local points do not lie on this divisor E?
Well, I have an E, and then I have a second divisor in the same class as E. So the E, let's say E1 and E2. So E1 gives rise to H1, and E2 gives rise to H2.
So for each point, at least one of the two functions does H.
Yeah, well, I mean, so happens for the two adic points, the second one always works. But there's no reason that should. In general, you sometimes use 1, sometimes 2, maybe 3, 4, 5. You know, it's very easy to, from one cycle, to generate a whole bunch of other linearly equivalent cycles. So you can very cheaply get as many H's as you want. So here we're sort of in the easy case where we can easily tell that something has local invariant 0. And yeah, 5-adic analysis. Is unnecessary. Since 2 is a 5-adic cube. So,
what's the reasoning behind that?
which one? Or here?
Yeah. Why is it?
Well, yeah, you don't have an extension. So we conclude that so I should just, well, maybe I should point out, well, one sort of general feature. So yeah, I mentioned this about So it's easy to generate linearly equivalent. So this is what leads to this. Second simple algebra that's equal in Brauer group first, and you can generate as many as you want. And so this is a feature of the analysis, so feature. In fact, we saw this yesterday a bit. Remember, I had the long equation for the two-torsion element in the Brauer group, and I think it ended with like y squared minus z squared, and then on the next line there was with the signs reversed, so minus y squared plus z squared, and I said they're equal in the Brauer group. So that was an example of this. And so, yeah, so, and then there's so obviously then they would be equal in Brauer x mod Brauer k, but then there's a straightforward way to calibrate them so they're actually equal in Brauer x. Okay, so this is one ingredient in the. I mentioned there's an effective algorithm to test the Brouwer-Manin obstruction to the Hasse principle and to weak approximation under these hypotheses on x. I kept repeating that x over k bar has trivial Brauer group, and that the Picard group is finitely generated. So that it's essentially a finite problem. And so under those hypotheses, then there's just a completely algorithmic way to compute these division algebras and to, so you have to come up with several representatives and for each element of Brauer group. And then, so that's one thing. And the second thing is, it's a bit bad that I started out talking about counterexamples to the Hasse principle, and I never mentioned what is perhaps the most famous example of failure of the Hasse principle, and that's the one due to Selmer. Yeah, so this is, I think, the most famous example of failure of Hasse principle. And I didn't discuss it at all. And in particular, I wasn't able to find out or figure out whether it can be analyzed along the lines of what was presented here. And that's sort of, I wish I did know, and it would certainly be a reasonable question for someone to ask, but the answer is, unfortunately, I don't know. Okay, someone says it should work.
There's a clever way to reduce it to that example? Taking a hyperplane section?
Yeah, interesting idea. Try to realize it as hyperplane section of this sort of example. Anyway, the classical approaches use some kind of combinations of ideal class groups, or, well, there's another approach where, you use this and then you relate it to its Jacobian, which will be, this is a genus 1 curve, and its Jacobian is an elliptic curve, x cubed, y cubed, and then you have a coefficient of 60. So anyway, there are classical approaches, but I've not seen it treated with cyclic division algebras. And yeah, thank you for listening.